Whoa. Let's calibrate that distance to the microphone. Good morning, everyone. Thank you for getting out of bed early enough to come to the first session. I was one of the last people out of the Uber party last night, so I thought everyone was being lazy, but I was informed that there were other parties which went on later into the night. So we very much appreciate you getting up at this relatively early hour for the last day of a conference. We have 4 very interesting talks today. It's my job as MC to try and put in awkward segues between the talks, but basically we're going to start with some segmentation work and then move into the full 3D construction pipeline. And of course, to do that, you need to know where you are, so we'll move on to some sensing talks about how you maintain a sense of direction, and also how you can do some range sensing as well. So to start us off, we have Renaud, who's going to talk about segmentation. And I have to start the video.
So good morning. I'm Renaud from the Autonomous Systems Lab, and I'm very excited to present our paper, SegMap, 3D segment mapping, using data-driven descriptors. So the goal of this work is to enable real-time SLAM for multiple robots equipped with 3D sensors. One of the first challenges that we're facing is that we need to recognize places visited by different robots. For this, we usually need a global localization solution, as we do not always know the transformation in between the robots. Then, single robot SLAM in large environment is complex enough. If we want to scale this to multiple robots, we will need to develop efficient strategies. And finally, this system generates lots of data, and therefore we seek a compact representation, which can easily be stored and transmitted between robots. So to address these challenges, we present SegMap. SegMap is a compact map representation based on 3D segments. By segments, we refer to clusters of points closed in space, which agree to some local properties. So the main idea of this work is not only to use this representation to enable localization, but also to reconstruct 3D maps and extract semantic information. So why do we even consider segments as the basis for our representation? Well, first of all, we believe that they can be a good compromise between local and global features. Then, when using segments, we do not rely on the presence of objects in the scene, and we also do not assume a perfect segmentation. Finally, when using the segments, it allows us to build this compact and descriptive map representation. So how do we do this? We've developed a data-driven descriptor for 3D point clouds, which first allows us to do global localization. So this is done by retrieving the segment descriptor in a global map using KNN, followed by a geometric consistency test. So to extract this descriptor, we have trained the CNN using a combined loss function, which addresses multiple objectives. First, we train for segment retrieval, using the N-way classification problem, which was introduced in the computer vision community. Then we achieve reconstruction by appending a decoder network, and we train the full network using a binary cross-entropy loss. And finally, we can extract semantic information by appending a very simple, fully connected network. So now we'll demonstrate our approach in a multi-robot scenario using the Kitty dataset. In the following experiments, the data from 5 LiDAR sensors is processed in real time on a single computer, which builds the map and estimates these trajectories. So in colors above, you see the segments which are extracted in the vicinity of the vehicles. Then we build the global map below by compressing the 3D structure to a handful of descriptors and segment centroids. These descriptors can then be used to reconstruct the environment and extract semantic information. Here we show the vehicles in red, the buildings in blue, and the rest in green. So once again, we perform localization by retrieving matching descriptors using KNN, which is followed by a geometric consistency test. So the lines that you see here represent matches, which are altogether consistent and lead to a localization. Note that we do not use the vehicles to localize, as these might become dynamic. So in this experiment, localization is performed at 10 Hertz, and a bandwidth of 60 kilobytes per second would be sufficient to transmit the descriptors. This is an effective compression of 44 times as compared to transmitting the full segment's point cloud. To conclude, I would like to briefly mention 2 other experiments where we achieved real-time performance by using the same network which was trained on the Kitty dataset. So for this, we used data generated by 3 UGVs, which were teleoperated by real FireMint end users in order to explore these 2 decommissioned buildings. So the 2 reconstructions that you see here could be generated by decoding the same compact descriptors which we used to do global localization. That's it from my side. Thanks for listening, and make sure to visit our GitHub, and I'd be happy to give you some more details at the poster session. Thank you.
All right, so for the young players in the audience, before we had GPUs, we had to do everything on just CPUs, and our next speaker, Lei Han, is going to tell us how we can do dense 3D reconstruction just using the humble CPU. Oops, let me just shut the last video because I got yelled at for not doing that. All right.
Hello, this is Lei Han, and I come from Hong Kong University, and I'm going to introduce our recent work on dense 3D reconstruction. And this system only uses RGB sensors as input, and merely requires a mobile CPU for computing. And as well know, dense 3D reconstruction has been proved to be great importance for many applications, including the mixed reality and also robot perception. However, there are still a lot of challenges left for this problem. For example, the localization drift in inside-out tracking systems may introduce significant artifacts for the reconstructed model. And also, in practical cases, we have to deal with the sensor occlusions, which may happen frequently in the practical cases. And yeah, so it's the local detection and the recover. And after the and besides, yeah, we would like to run the reconstruction system on portable devices where the portability and the computational power are highly constrained. And there are already extensive work has been done on this project, on this area, like the elastic fusion and bundle fusion. They achieved the state-of-the-art reconstruction quality, yet require the high-end GPU for computation. So in this paper, we propose the flash fusion, a faster, large-scale, high-resolution, dense 3D reconstruction framework. It follows a quite classical SLAM pipeline. We use RB features for feature extraction, and which is later used for loop closure detection and globally consistent localization. Actually, camera poses are estimated by minimizing the alignment error of the feature pairs. You will see in the next slide. Yeah. So this cost function is more complex than the post-graph optimization, but it leads to higher accuracy and robustness. So examining this cost function, it's like for each frame, we have to find its corresponding frames that share an overlap area, overlap the view with each other. And it's like this. And for each frame correspondence, we register the two frames using sparse RB features. And finally, camera poses are estimated by minimizing the alignment error of all feature pairs collected. Generally, this cost function is solved using nonlinear Gauss-Newton optimization. So firstly, we compute the Jacobian matrix, then followed by the computation of the normal equation, which is further solved to update all camera poses. Most methods compute J transpose J directly for efficiency, yet it still remains time-consuming because in this step we have to traverse all the features one by one. And fortunately, we have proved that the summation here is only a function that depends on the camera poses Ti, Tj, and also the second-order statistics of some feature positions. So note that for each frame pair, we could have maybe 100 feature pairs inside. And the second-order statistics is only need to be computed once and reused later. And it is worth noting that in our proof, there is no approximation. So we achieved the state-of-the-art accuracy. And as a result, we can do the localization very efficiently, like using CPU and at 50 Hertz on a single CPU core. And we show the results on the TOM IGT dataset and also the ICL-NOM dataset. Yeah. And the accuracy is comparable to state-of-the-art. And for the real-time reconstruction, we also propose several techniques, like the sparse sampling technique, to identify chunks that need to be processed efficiently. And also, we recognize the highly organized data structure in the matching cube algorithm. So for the real-time CPU computing, we integrate frames at the real-time frame rate, while update the 3D models at the key frame rate merely. And this is a live demo of our online reconstructed model. So for more information, you can visit the website, and also the code will be released on the GitHub. And thank you for your attention. Thanks.
All right. Now, I know everyone's hanging out for the award session this afternoon, but we all know one of the most prestigious awards is the paper with the longest title, and our next talk is definitely one of the contenders for that. I will read it. It's Adaptive Bias and Attitude Observer on the Special Orthogonal Group for True North Gyrocompass Systems, Theory and Preliminary Results, and it'll be presented by Andrew Spielvogel.
Hi, my name is Andrew Spielvogel, and I'll be presenting my work on an adaptive bias and attitude observer on SO3 for True North Gyrocompass systems. So the problem we're trying to address is the estimation of true north attitude while only using angular rate and linear acceleration measurements. We separate this problem into two parts. The first part being doing real-time estimation of measurement bias in 6 degree of freedom fiber optic gyroscope IMUs. In the second part, doing attitude estimation directly on SO3. The motivation behind this work is for doing precision navigation for scientific survey missions, and also for doing navigation in GPS-denied environments or magnetically compromised environments. So it is important to note that the heading that we are estimating is true north heading. So that is heading with respect to geodetic north as opposed to the commonly used magnetic north. So we're not using magnetic compasses or magnetometers to estimate magnetic north. Instead, we're using linear acceleration and angular rate measurements to estimate true north directly. We define our measurement model to be as following, where the angular rate measurement consists of 4 terms. The first term is due to Earth rate, which is 15 degrees an hour. The second term is the angular rate of the vehicle with respect to Earth. Our third term is a constant bias term, and our fourth term is zero mean Gaussian noise term. Similarly, for our linear acceleration measurement, we define it to have a term due to gravity, a term due to the vehicle's acceleration, a constant bias term, and again, a zero mean Gaussian noise term. In MEMS IMUs, the Earth rate term is commonly dominated by the noise term, and it's common to ignore the Earth rate term in your measurement model. However, in fiber optic gyro IMUs, the Earth rate term can be detected, and this makes the bias estimation problem much harder. Our gyro system, our gyrocompass system is consisted of 2 observers, which we can see here. The 2 observers are the first stage we do sensor bias and north estimation, and then we pass those bias terms into our attitude observer, which estimates rotation from the instrument to northeast down frame. So together, this system has only 2 inputs, which are the angular rate and the linear acceleration measurements. So we're not using any magnetometers. And the output is the rotation matrix. We evaluated this system with 3 numerical simulations. In the first simulation, the instrument experienced no rotation. And in the second and third simulations, the instrument experienced changes in heading. We see that in the second and third simulations, the biases and the attitude converge to their correct values. However, in experiment 1, they do not. This is due to the fact that the convergence of the bias terms is dependent on excitation of the system. And since the instrument was experiencing no rotation, there is no persistence of excitation to drive the biases to their correct values. In addition, using the JO2 ROV seen here, we conducted a preliminary vehicle experiment in the lab, where the vehicle experienced heading changes similar to the numerical simulations shown before, and we were able to demonstrate that convergence of the attitude to its true value and the bias terms converging to constant values. In conclusion, this paper reports a stable adaptive observer for measurement bias in 6 degree of freedom fog IMUs, a stable attitude observer directly on SO3, and a true north gyrocompass system that links these two observers together. Future directions that we're currently going is trying to improve the convergence time and experimentally evaluating. Thank you.
All right, so for our last talk, us who are still in academia don't have the big budgets of the big companies. So when we buy a $70,000 LiDAR, we'd like to get as much value out of it as we can. So our next speaker, Sanjeev, is going to tell us some really clever hacks, I would say, to get the most out of your sensors.
Hi, I'm Sanjeev, and this paper is about LiDAR. So all of you know about commercial LiDAR systems, and most of them spread all their points out equiangularly. So this image from the Velodyne LiDAR has so many points on the road, and it's usually flat. So maybe we want to put a lot of our points on targets, like car and pedestrians. So here's a scan from our sensor doing a traditional scan. But what we can do with our algorithms is that we can place all the samples either on the flower or on the bottle. So we can do LiDAR zoom. And so there's been many different LiDAR algorithms in the past. Most of them have a fixed steering for the beam. But recently, there have been works from the computational sensor community which brings in programmability into the game. And that's what this paper is about. It's about bringing programmability in the angular domain, controlling where the LiDAR is scanning. So our ray diagram consists of a computer that controls a single MEMS mirror, and it's scanning a LiDAR over the scene, and you can control where it scans. Our particular system is made up of an open source LiDAR, which has a transmitter and a receiver. And the transmitter reflects off a commercially available MEMS MEMS mirror, and the receiver is defocused over the field of view. And we control the MEMS with voltages. Now I'm going to abstract away this device as a single dot with a field of view to explain how we do calibration. Calibration is done by placing 5 planes in our working volume at known distances, and then we can reconstruct anything in the working volume, including this other plane. We have plus minus 1.5 centimeter error. Now I'm going to talk about how we control the LiDAR in this field of view. We do it with 2 parameters. The first is the distance between samples, the angular separation, and the second is the viewing direction. So with angular separation, I'm going to show you a few deblurring applications. And I'm going to start with this very simple scene with a sharp protrusion in simulation. And the measurements are wrong. They're blurred because the measurements are correlated. But we can invert this matrix. We can deblur this scene. We can get back the measurements. And in reality, we can do it as well. So here's 2 planes separated with a scan. And you can see hallucinated measurements between the planes. But we can deblur that. We can remove that, make it a lot sharper. And we've shown other matrices that are invertible for other optical configurations in the paper. Now, most of the remaining results I'm going to show you are viewing control results, and they're based off of this algorithm. And the algorithm says that if you have a scan of the scene, you break it up into boxes, and each box you give it a score. It's like an occupancy map. And then you generate candidate trajectories over the scene. And you pick the best one according to a information theoretic metric. Now, we're taking a robot planning algorithm, but our MEMS mirror is the robot here that we're controlling. Now, this allows us to do many different applications. For the first application, I'll show you smart zoom. So the user selects a region, and we decrease the cost of the boxes there. So here's a sort of generic scan of the scene, and a naive zoom would put all the samples on one object or the other. But our smart zoom zooms onto the flower, but still keeps some points around the scene. The second application I'm going to show you is energy-aware adaptive LiDAR. So I'm going to show it with this simulated scene with 3 objects. And we give a cost to each box depending on the distance of the objects, their velocity, and their complexity. And so here's ground truth of that scene with 3 objects. And here's the score of every candidate trajectory across that scene. And it's the worst scan and the best scan. Now, the best scan has a lot of points on the neck of the vase, which is complicated. And the worst scan has too many points on the bottle, which is far away and simple. We've also shown these kind of results for real scenes that you can see in our paper. Now, our final application is about gradient-based reconstruction. So if you have this mug and you subsample it, you can take groups of samples, calculate the gradient, and reconstruct the original mesh. So this is well known in vision and computer graphics. It's gradient-based reconstruction. You can do it for many other different objects in simulation. But my point here is that we can actually do this in reality with our sensor, right? So we can place our samples where we need it for gradient-based reconstruction. So here's 2 planes, sort of a base scan. Instead of doing this, we can do a new experiment. We can put our samples in the depth edges, right? So it's a new scan. And in post-capture, we can reconstruct the scene with much better fidelity. So our hardware has some limitations that I think we can improve, but our algorithms are general for any directionally controlled LiDAR. I can talk more of that in the poster. I'd like to thank our collaborators and the NSF, and thank you all for paying attention. Thank you.
All right, we'll invite all the speakers back on stage so you can grill them with questions. We have 3 colorful cubes that can be thrown upstairs. So have at them with your best questions. Stick a hand up if you want to ask a question. I know it's early. Some interesting talks. Do you have any questions? Otherwise, I'll get it started. All right, I'll get it started. So, Sanjeev, you've shown a lot of the effects from the perspective of the system with the LiDAR on it, right? Does anyone actually know what would happen if you have 1,000 cars all within a constricted space, each with their own LiDAR sensor? And could you potentially use your method to avoid impinging directly on the other cars' LiDAR sensors?
Absolutely. So multi-path interference is a big problem with LiDAR in the space. So if you're tracking all the cars, if you knew beforehand where the LiDAR was on the other cars, definitely you could have regions of no sampling, so you would not directly sample. So that is definitely one benefit. In terms of multipath, we'd have to work on modulating the LiDAR. There's some work on that we haven't done, but other people have done. But definitely for the direct interference, this could definitely have an impact.
All right, thank you. Questions from the audience? Aha, thank you, kind sir. All right, so this is the blue cube. Blue cube, please.
I just have a question for the last speaker. Based on the cost map that you defined for the occupancy grid, was that a automatic synthesis of some cost function, or did you have to do some heuristic tuning?
So if I understand the question correctly, it was about the cost function for the adaptive LiDAR. So if we look, for example, at the energy-aware adaptive LiDAR, the cost function for each of the components, for example, if something is too far away, there's a 1/r² fall off, and maybe you don't want to spend that energy. Those are all closed functions. For example, for velocity, you can calculate if the object is going to leave your cone that you're moving in. So each of those are closed form, but definitely the way you weight them all together, that's heuristical depending on your application. Right? How much do you weight distance versus velocity? There's a heuristic component to that.
Questions? Thank you. Green cube, please.
So this question is for the segmap, segmentation.
Yes.
So do you have to train your algorithms for getting the descriptors for every different map? So you showed like 3 different maps, right?
Yeah, so for this it was trained on the Kitty dataset. So a separated run than what was used for this multi-robot experiment. And the same for the 2 search and rescue scenarios. We used the same model which was trained on the other dataset. And this one is actually using a different segmentation, and was still working nicely there.
Thank you. We had a question back. Blue cube, please.
For the true north, what? I was wondering, what other extrinsics do you need to recover this information? Do you use like the Earth's radius? Or can you talk?
Can you talk louder? I can't quite hear.
Sorry. For recovering true north, do you also need to include things like the Earth's radius or other factors like that?
You need to know the Earth's radius in the latitude of the instrument.
The latitude. Okay. Cool.
Yeah.
Awesome.
Questions? All right, I've got one for Lei. So you showed some really elegant, fairly efficient compute on a CPU.
Yeah.
If you're willing to give up some more further performance in terms of reconstruction accuracy, how much could you scale it down further in terms of CPU power?
Not sure. There is a photo, there is a picture demonstrates the time cost of each procedure in my algorithm. And I didn't fully get your question. Can you repeat that?
How low could you go in terms of the computational power and still get some sort of usable reconstruction out of your system, maybe at a lower resolution or a lower frame rate?
Sure, it goes like from the cubic order. Yeah. So if you set the resolution at 0.5 millimeters and compared with 1 centimeters, you look at maybe 8 times speed up. Yeah.
Thank you. We have time for maybe one more question from the audience. Orange cube, please.
This is for the True North talk again. What level of accuracy were you able to get experimentally?
We were able to get within a degree of accuracy. Yeah. Hopefully, we're hoping to get better than that in the future, but in this experiment.
Maybe one last question if we have a chance. Okay, I'm just going to selfishly ask one question. So I think a lot of people who study navigation research do it because they don't really navigate very well. So what is the sort of rule of thumb difference for true north versus a magnetic north in terms of when does it sort of matter a lot and in what sort of applications? I know you touched on it in your talk.
So the motivation behind our work is for doing underwater robotics, and estimating heading error is one of the main culprits in your navigation error. So the motivation behind our work is for doing high accuracy underwater survey missions or some other underwater mission which you need to have high accuracy navigation. But also it could be extended to anywhere where there's a magnetically compromised environment.
All right, just in the interest of time, let's thank our wonderful speakers from this morning.